My name is David Biello. I'm an editor at Scientific American, the United States' oldest continuously published magazine. Not just science magazine. Anyway, that's the advertisement. So we're here to talk about energy, water, and agriculture. There is a word missing from that list, I would stipulate, and that is land. As a colleague from Monsanto put it yesterday, conversations in the future are going to be about the best use of every acre. And that best use of every acre is going to principally revolve around these issues: energy, water, and agriculture. And I'm just going to throw out a few numbers to kind of set the scene for my esteemed panelists. First and foremost, on a food crop basis, it takes 1 liter of water to produce 1 calorie of food. That's a dynamic that has not changed, and that, frankly, we haven't worked on. So there is one room for improvement. The number 2 use of water right after agriculture and the production of all those calories is, of course, energy itself. I'm talking about water cooling for thermal power plants, but I'm also talking about the water used, as we heard from President Clinton, for hydraulic fracturing or to get those wonderful oil out of the Bakken Shale in North Dakota. Finally, and perhaps most importantly, we are looking to ask our agricultural sector to take on a 4th F, as the departed Norman Borlaug put it. It already produces food for us, feed for animals, which really is food for us, and fiber. And that we have essentially taxed our agricultural sector almost to its limit to provide those things. And we're going to add a 4th F, fuel. Dr. Borlaug was not sanguine that we could do that, but hopefully this panel will help us understand how we might. And without further ado, I'll pass it over to you. Yes. That's right. I'm also doing tech support. Let's see. I think this is the clicker. I don't know how to use it, though. Let's see. Oops. Where are these loaded? Of course, one can never find the slideshows when one wants to. There you are. Okay. There you go.
Okay. Thank you.
I'll do that for all of you.
Thanks. And thanks to Cheryl Martin from ARPA-E for inviting me to this. It's not my orientation or my nature to speak publicly. I don't like to do it, especially about the stuff we're doing, but this is such an interesting topic and it matters so much to me that I thought I would share the high-level ideas and hopefully ultimately just answer any questions you guys have. Briefly, Kleiner Perkins is a global investment firm, a venture capital firm, and we focus on new innovation that can completely and totally transform industries. And about 5 or 6 years ago, we started investing in what we call green technology. And a lot of that is energy, but related, supply-side energy related, but it also has to do with a variety of other factors related to the environment, including water and, of course, sustainable agriculture. And certainly the confluence of all of those really matters to us. Myself, I'm a chemical engineer. I'm an entrepreneur. Started a number of businesses, a few you'll hear about today. And I sit on the board of companies in this space. So 2 companies in the water sector, 2 companies in waste recovery, one of which is related to agriculture and returning food waste to agriculture. And then a third, which is in a category we call transformative agriculture. And I'll walk through a short presentation for you and then obviously take any questions you have.
Introduce yourself.
Oh. Amol, and by the way, he asked me to introduce myself. My name is Amol Deshpande from Kleiner Perkins, in case I didn't say that already. So what we're really looking for is big problems and then big ideas to solve them. And I'm going to go through kind of some of the things we've looked at and what might be sort of at top of mind for an investor. If you're looking for something that's a bit counterintuitive but sits at the confluence of these factors. Some of the big problems that we see, a need for water as a result of drought and, of course, increasing population, increasing consumption of that water due to needs for nourishment of people and for industry. Agriculture as a source of contamination for water supply. So if you're familiar with a variety of issues in chemistries, things like oxidized contaminants, which can be a result of agricultural runoff, which can contaminate water supplies. And I'll talk a little bit about how we look at that problem as it relates to water scarcity, because there's some very obvious solutions I feel like people have not looked at. In agriculture, this is something that I spent a lot of time with. I worked at Cargill, besides being an entrepreneur in the ag sector. And it's lack of germplasm or quality seed for crops, and particularly in emerging markets, but it can also be in the United States. You'd be surprised the difference in the quality of crops that's grown around the world, and actually just simply the availability of those. The energy potential of food waste, we waste a lot of food, and recovering the calorific value of it has a great deal of potential. There's also nutrient potential in that we can return to the land, and we'll talk a little bit about that. And the final thing, which encompasses the last 2 points, or 2 of the last 3 points, which really matters to me, is I think if you look at the whole chain and you piece it all out, you say to yourself, what is the biggest bottleneck, what is the biggest constraint? In my opinion, it's the existence of 600 billion or 60 billion livestock on the planet every single year. So if you want to talk about agricultural land use, water use, energy use, it really boils down to one thing. It boils down to livestock. And if you look at the constraint in the system, you can make solar energy to whatever final transformation you want, as efficient as you want, but an animal has gotten about as inefficient as it can be through animal husbandry over many years. So kind of that's, to me, is if there's a place to attack the problem, that is where I would attack it, to be honest. And I think actually everything else is sort of minor in comparison to that. And certainly I can share with you a bunch of statistics about that. So some big quick ideas, and then I'll try to spend a few more minutes on the last one, and then obviously take any questions you have, but after we've had a chance to hear from the rest of the panel. A lot of people think of water recovery and the source of water as, for instance, desalination. Desalination is a very energy-intensive way to provide water. Well, it turns out, based on our research, agriculture has contaminated water wells all across the United States with a compound called nitrate. There's other contaminants in there as well, which are oxidized contaminants. Nitrate is directly caused by agricultural contamination. By our count, there's probably thousands of wells in California that are contaminated and shut in due to nitrate. Okay, so you're building desalination plants, and it's costing you $1,200 an acre foot to recover that water. It's highly energy intensive. Meanwhile, all you ever had to do was find a way to very effectively treat that nitrate, and you can recover water wells. We actually have a company that has an innovative biological technology to do that, very low energy technology. So that's sort of, I think, recovery can solve a lot of our problems. Maybe not all of them, but a lot of them, and certainly in a more energy efficient way. I think removing waste is a huge thing. Landfill is just a bioreactor that accidentally produces energy. There's a lot more active ways to do it, and food waste is gigantic. There's something like 30 million tons of food waste thrown away every year. It all has a lot of calorific value. There's other organic waste that can be recovered as well. Again, a little bit of a smaller dent in what we're trying to do, but I think quite an obvious thing to do. And we have a company that does that as well. And the final thing is, I think we have to find a way to replace animals as a source of protein delivery for humans. I mean, I don't think the planet can subsist, and certainly growing populations around the world can't subsist with the amount of livestock that we have. As I said, they're inefficient naturally, and they've gotten as far as they can go through animal husbandry. So these are a few of our companies. APT is one that does recovery of nitrate from water. Harvest Power is one that recovers energy from food waste. Both of these companies have grown to hundreds of employees now, have legitimate businesses and producing profitably and growing and competing very effectively with incumbents in their industries. Sinor is a water business in China, which is doing the same thing, water reuse and recycling, because the problem's no different over there. And the one you see in the bottom right-hand corner is a new technology we've invested in, where we have a way mechanically of replicating the texture of meat perfectly using plant-based proteins. And we think that that's a real breakthrough innovation. You'll hear a lot more about that in a month or two. And again, it goes back to the issue of attacking the real core inefficiencies. So it's just a little bit about what we do, big ideas in this area. Again, I'm an investor, a venture capitalist. You're going to hear from some real scientists, people with actual facts, and happy to take any questions you might have. Thank you.
All right. So next up will be Molly Jahn from the University of Wisconsin-Madison, and I will endeavor to get her panel presentation up here. I would point out that he just made a very important point about energy and water, which is that just as energy requires a lot of water, water requires a lot of energy. In fact, it is the #1 user of energy. Take it away.
Thank you, David, and it's a great pleasure to be here. My qualification to be standing here is I am a plant molecular biologist by training, plant breeder. I launched into agriculture intending to save the planet through better crop varieties, better use of lands, better use of inputs, and had some success. I've got varieties commercialized on 6 continents and realized that was never going to be enough. So I went from that role to serve as Dean of Agriculture, one of America's top College of Agricultural Sciences at University of Wisconsin-Madison. From there to Deputy Acting Undersecretary at USDA, and from there to an at-large role serving my provost as his special advisor for sustainability sciences. And it's really from that synthesis of experience and approaches that I will make my remarks. As a dean, I hung around with other deans, and my engineering dean said, give me all the water in the world, I'll give you all the energy you want. Give me all the energy in the world, I'll give you all the water you want. But agriculture sits right in the middle of all those equations. And that is, in fact, right where it has sat in my experience. The top-line message of the remarks I want to make to you today is that we have a new frame for agriculture in this century, in this country, in the developed world as well as in the developing world. And David already said something really important. That new frame for agriculture requires us to shift from focusing on local yield maxima of staple crops to the management of agricultural ecosystems for sufficiency now, and that sufficiency is a human construct, and for our needs now and later across scales. That shift in target is profound, has profound consequences for the way we innovate, for the way we manage lands from local to global. And one very critical, and it is all about choices we make on landscapes. In short, we need to move agriculture from a fundamentally extractive process to a process that is about regeneration. We need to move agriculture from a process that is about local maximized outputs to a set of sufficient outputs and outcomes, recognizing the very important role that agriculture plays as a form of planetary care. So, if that's our challenge, and it's a big one, what is the evidence that there's room for growth and optimism, mandates for innovation? My first slide, these are 4 photos sent from, it is a dairy farmer. In fact, it's a Wisconsin dairy farmer. And I'll acknowledge our previous speaker's point, which insofar as we in agriculture are meeting demands, those demands themselves, that is the demands of diet and diet-related choices, can shift, and we must consider the role that diet plays in terms of the pressure agriculture puts on the planet. This dairyman, he's in the business of generating protein. He received his farm from his grandfather. He's third generation on this farm, intends to pass it along. In 1997, he had 60 cows. In 2001, he realized the imperative of climate change. And one very important message that I have for those of you innovating in this space is there is tremendous diversity of opinion, regardless of the politics in this country. This dairyman in business, making short-term profit, has completely renovated his dairy operation to take advantage of the waste and to manage nutrient cycling, to optimize his performance as a business. And so I have 4 slides here that really show the types of investment this man has made within an ordinary dairy. He's moved from 60 cows to 2,800 cows milking head and 2,200 heifers. He became concerned, as I said, in 2001 with energy issues, so he turned to the waste and wastewater and innovated. He innovated on farm. And for those of you looking for great investments, don't overlook American farms. He's got a digester here that he, with colleagues, designed and built through reverse osmosis. On the upper right, there are the 5 different streams coming out of this, with about 50% of the water recovered so he can drink it. There's a picture of him that National Geographic has of him drinking the output of this system. He has captured waste beyond the out of the waters that you can't drink. He's got algae that he recycles back into nutrients for feed as well as energy and other products. And in the lower right on his dairy, he has built an aquaponics greenhouse as well as an aquaculture operation. And so while we're transitioning to products like Arul has described, there is tremendous opportunity even within the current structures and incentives of agriculture for this type of innovation and profit. And so John Vries in Baldwin, Wisconsin is living proof. Now John scales up. So a very exciting thing I've had the opportunity to support from my roles, both academic and government, is the call from within farm gates, both in the developed and the developing world, but particularly in the developed world, for better within farm gate decision support connected to sustainability, where sustainability simply means getting what I need now and having enough for later. Really, though, there's an additional commitment that most farmers like John bring forward, and that is it's not about maintaining, it's about improving. It's not about stabilizing, it's about growing, but it's about growing within limits. And so I see another very exciting trend. With it, to answer that demand, we are seeing commodity-focused sustainability investments aggregating. Next month in Denver, March 15th and 16th, an unprecedented meeting across American agriculture will occur under the moniker the National Initiative for Sustainable Agriculture. These are the major American commodity groups: livestock, commodity crops, specialty crops, coming together to call for setting new targets and hitting those targets within, as far as better management and better value from overall agricultural operations. These 2 on the right are 2 of my recent PhD students. They are entrepreneurs. They have a little company called Ag Squared. They're agricultural, but their commodity is information. And so a second important point I want to make connected to opportunity is that it isn't just about outputs, it's about outcomes. We need better information systems, better information management, tools to scale, tools to bound uncertainty. And these 2 young people have launched off. One's from Harvard, one's from Yale. They were both supported by the National Science Foundation for their PhDs. And this is the means by which they have elected to head off to save the planet. They're looking for capital. They're looking for about $2.5 million, and I can't wait to see what these guys do next. In the meantime, the one on the right, who's from Harvard, has started Harvard Alums for Agriculture. The skill set, the excitement, the imperative, the urgency of the challenges we face globally are apparent across the board, and I see new talent flooding in to answer the call that the National Initiative for Sustainable Agriculture is putting up, not just to maximize efficiency in agriculture, but to fundamentally change the targets we're aiming at in agriculture from both human sufficiency and planetary care. So the last set of remarks I want to make are about some things beyond this that I watch happening that I think are incredibly important for all of us who understand the nexus we're here today to talk about. About a year ago, I was identified to represent the U.S. in a commission focused on sustainable agriculture and climate change. That commission, working to influence global processes, that is the Durban and Qatar community or meeting of parties on climate change, as well as Rio Plus 20, the G8 and the G20, all major global fora focused on agriculture, have come together to issue these 7 recommendations. They represent a global framework towards partnership. They acknowledge the role that dietary choices make. They acknowledge the importance of managing waste and recognize that a lot of people make a lot of money wasting in our current food systems. So these imperatives are going to require significant innovation and opportunity, as well as significant policy adjustments. Under that framework of 7 recommendations, it is a call to partnership. And so I'm going to conclude with one of our relatively recent entrants into a collaborative team. Tony Janetos here at the podium is also a member of this team. Because these issues of agriculture, food security, water, energy, these issues are critically important for the quality of human life, but also, of course, for national security and civil stability. And so this is a unit that's come in to help our team focused in these areas on the civilian side, connected to best management of agricultural ecosystems. This is a unit that has learned how to put information together in a military context to move from descriptive to predictive capacities, to begin to mobilize the vast amounts of information that are relevant to the challenges before us in agriculture as they connect to water, to food security, and to energy, towards managing our systems with better quality outcomes through these radical partnerships that are taking place, answering the call of agriculture to do a better job both meeting our needs as a form of a human lifeline and as our dominant form of terrestrial planetary care. Thank you.
All right. Nice round of applause, although I'm gonna hold my applause because you mentioned a competing magazine. Apparently we've been hanging out on the wrong farms. We can say with some assurance after the talks this morning that the military is one of the primary customers for this new fuel from agriculture, and has already flown jets and powered ships with actual agriculturally produced fuels. And I'm not talking ethanol from corn. I'm talking biofuels from or biojet from camelina, and even algae and other products as well. I will next turn it over to Tony Janetos, who got a shout out in that last presentation. He is from the Joint Global Change Research Institute. Tony. Oh wait, I should help you.
Yeah, you should. Otherwise, I'm going to have to talk to the DoD logo the whole time.
Oop. Are you still adding text?
No. That's good. Great. David, thank you very much, and thanks for the opportunity to come here and talk. I direct an institute that's primarily devoted to trying to understand the complex and quantitative interactions between the way we use land, how we produce and use energy, and increasingly the role that water plays in that interaction. We do that primarily through the development of a family of models which are called integrated assessment models, for which our main model is called the Global Change Assessment Model. And these historically have focused on the connection between human systems and human decisions, primarily in the energy sector, and greenhouse gas emissions. And they've been used over the years to look at the consequences of different potential climate policies, on the energy mix, on emission scenarios. But increasingly, over the last 5 years, they've played a much bigger role in trying to understand the interactions amongst these systems themselves. And in particular, as we've heard already, one of the questions of the future, which is actually beginning now, is how are we going to use all those last acres of land? Because now we use the land not only for food production, but we increasingly use it for energy. And that combination of forces, of decisions about energy production and food production and how those compete for land resources, turns out to be a surprisingly important feature of trying to understand not only how the present works, but how the future might evolve. This is just a little cartoon of sort of some of the topics that these models are built to address. In our institute, over the last 5 years, we focused particularly hard on the land use question, and so we now have a fully functioning land use allocation model that works within the context of the global change assessment model, so that we can look at quantitatively at the interactions between energy demand, changes in the climate system, changes in climate policy, and constraints on how we use on agricultural production for a wide range of crops, including bioenergy crops, and the use of waste, both municipal solid waste or agricultural waste, to feed the energy stream. The next challenge, however, is making sure that water is incorporated in this framework in a quantitative way. And I promise not to go through this slide because we don't have 2 hours. But I just want to show it as a summary to say that we're now within the construct of this modeling framework. We have an explicit representation of the water sector, both in terms of demand, both for agricultural demand and demand in the energy sector, and in terms of supply. We've actually built a monthly water balance model so that we can actually look at a large basin level, not only how these interactions work now quantitatively, but how they could evolve in the future, not only as a result of changes in population distribution, demography, diet choice, but energy choices and change in climate as well. This one illustration on the bottom shows you in a case where there's no climate policy, potentially what happens over time for water demand for electricity generation. And what you're seeing here in terms of withdrawals is actually the result of changes in the underlying technology, in the technological mix as we see economies, in particular the energy economy, become more efficient over time. The second major thing that we're doing is we have worked now for about the last 8 months on a major report, which is due to be finished actually this week, on interactions between energy, water, and land systems. This is part of an interagency effort for the new National Climate Assessment. This is just a schematic from that report, but it looks at case studies and at some of the theoretical interactions between these systems, energy system, water, supply and demand, and land resources in the context of both climate variability and climate change. The last thing I want to talk about are just a few observations from not only the work that we've done so far, but general observations from the current literature. Agriculture is by far the largest user of water in today's world. It's about 70% of withdrawals. It's 85% of the consumptive use. Bioenergy crops can potentially become an important source of water demand in the future. We've done a number of studies that show that depending on how one values carbon, the spread of purpose-grown bioenergy crops can become very, very large. If carbon is not valued, then we are likely in store for an extremely large and active bioenergy crops that will actually compete with food crops for productive land. If carbon is valued, we'll still get a lot of bioenergy, but we won't get as much purposely grown crops. The demand for water is going to grow over time. That's a simple function of the fact that we're going from a population of 6 or 7 billion people to a population of somewhere between 9 and 10 billion people globally over the next several decades. Most of that demand growth for water is going to be in the developing world. We'll see some of it here. The OECD countries will see some of it, but most of it will be in the developing world. And much of the developing world is already under significant water stress. The energy systems themselves, because energy demand will also grow, will become a large and larger source of withdrawals. And the cooling demands for power generation, which is the largest single use in the energy sector of water, are certainly going to grow in the future. And again, most of that growth will be in the developing world. So one of the lessons from that I take away from these, in a sense, simple observations are the technologies that affect how water is used in the energy sector in the developing world are going to be particularly important. They will be a game changer for the availability of water for many, many different uses. New cooling technologies, of course, could dramatically reduce freshwater withdrawals. Paradoxically, depending on the particular technology, they could end up increasing the consumptive use, but the consumptive use of water by the energy sector is much smaller than it is, for example, for agriculture. Our next step as a modeling community is to really understand the allocation process of water amongst competing users. This is driving our economists a little bit crazy at the moment because it's not a well-posed problem for them. But it's nevertheless an important problem to really understand, both regionally, locally, and nationally, because that then will determine who gets the water they need for which purpose. And that will shape this interaction going into the future. Thank you.
All right. So what we can take away from that, I guess, is water stress is a fact of life, for better or worse. And here I thought air cooling in China was gonna save the world. Next up, we have Ellen Williams, who is the chief scientist at BP, a perhaps unknown to you oil company. And here's her presentation.
So thank you very much. It's a pleasure to be here. So I'm Ellen Williams. I'm a former university physics professor. I spent 30 years in academics, mostly at the University of Maryland. 2 years ago, I left academics and joined BP as their chief scientist. One of the projects that I've been working on at BP is looking at issues of sustainability. Some of you may know that BP has a long history of considering and thinking about climate change and what that might mean about our ability to meet the world's energy needs in the future. Recently, maybe the last 5 or 10 years, people have become increasingly aware that water stresses, land stresses, basically all driven by growing population, also could pose a number of threats. And the purpose of my work has been to take a look at that in the context of what those stresses mean in terms of energy. Will those stresses actually impact or hurt our ability to deliver the world's energy, or will it cause us to change the choices that we might otherwise make about what sources of energy to use? And I can tell you, as with almost all the good research projects that I ran as an academic, I went into the project with some pretty strong ideas about what the outcomes were going to be, and was in some cases quite surprised by what we learned. So we did this project as an open collaborative research project. We brought together scientists from a large number of universities. I used to have the logos of all the universities there, but I had to take them off. Our legal department said I wasn't allowed to use logos, which was too bad. It was a much prettier slide before. So we had about 13 universities addressing different aspects of the science and technology of the energy delivery systems. And this has been a very amazing learning experience because I've been dealing with chemists, engineers, hydrologists, agronomists, economists. A whole breadth of different types of disciplines have to be engaged to understand these types of results. I'm going to reiterate many of the words you've heard from others here. When we start to talk about energy, water and land, we encounter very emotive issues. These are things people rightfully feel very strongly about, in large part because they are so regional. The impacts of water scarcity can be very, very intense in one region, whereas in another region, water issues may not be a problem at all. So I'm going to show you some world average results from our work, but please keep in mind that while these are world average results, they do not reflect, although we're aware of, the fact that regionally things may be very different. Okay. So we looked at how much energy or how much water you had to use to reduce energy. We looked at how much energy is used in dealing with water. We looked at water for land and energy for land. And I'm going to start out with energy, water for energy, because that's the one that seems to have the easiest to describe and have some of the biggest impacts. Okay, so on the left here, this is what a standard prediction of how much energy we're likely to be using in the future. So right now, 2010 or so, we're using 12 billion tons of oil equivalent. That's an energy unit. I can change it to other units if you'd really like. But the key point here is that in the next 20 years, we are certainly going to see that demand for energy increase dramatically. And it often surprises people to see how little of the world's energy consumption right now comes from renewables. It is a small fraction. It will increase dramatically over the next 20 years, but it's increasing from a small base. So it's going to take us a while before we get to the point where renewables are creating a large amount of the world's energy. In the meantime, we're using a lot of fossil fuels and will continue to do so. So one of the things that we looked at in our study was exactly how much water are we using in producing fossil fuels and burning fossil fuels to produce electrical energy. So the graph on the right illustrates what we found. So you should be aware that the world has available, in terms of renewable fresh water, about 40,000 cubic kilometers per year available for people to draw. That's rivers, lakes, and renewable aquifers. The world is using right now, withdrawing from that reserve, about 4,000 cubic kilometers, about 10%. If you look at the amount of water that's used in producing energy from fossil fuels, I've broken it down into different categories. Extracting fossil fuels, mining coal, getting oil out of the ground, getting gas out of the ground, even the notorious fracking process, all of them locally can use a lot of water, but in terms of the global average, the amount of water that is used to produce fossil fuels is very small. Less than 1% of the world's total water withdrawals go to producing fossil fuels. If you then look at the other big use of water, or at the big use of water in the energy industry, that's water used for cooling in the generation of electrical power in electrical power plants. And that's a bigger number. You can see it's about a little over 400 cubic kilometers in 2009 of water was used, was withdrawn for use in electrical power plants. And so that's about 9 or 10% of the world's total water withdrawals. That water is often used in cooling plants that just take the water in, run it once through a cooling cycle, and dump it back out into a river a little bit warmer. That can be very disruptive to local ecosystems, and it is a water stress. So if we take what we know about how much water has to be used in those cooling systems and project into the future, assuming that people use the same technologies in the future that they're using now, we would get to the bar in the middle right there, marked as 2030 BAU. And so you can see that if we just keep on doing things the way we're doing them now, the world water withdrawals for cooling in electrical power generation will increase from about 400 to about 600. So we will see a big increase in the water withdrawals. But that's assuming that we use once through cooling. There's another technology called wet tower cooling. It's not a new technology, it's an old technology, and many of the world's water plants use it now. If all of the world's electrical cooling plants, electrical generation plants, went to once through cooling, a known existing technology which is actually not more expensive to put in place, then you could move over to the right-hand side there where I say technically feasible. The world's water withdrawals for producing electricity could be reduced to about 50 cubic kilometers, a relatively small fraction of the total world water use. That, of course, isn't going to happen instantaneously because there's infrastructure in place. There are lots of once-through cooling plants, and they're not going to be taken down right away. But within our hands right now, we have the technology to move in the future in new builds to much lower water use in power production. Okay. So now I can't go in detail through all the different things that we looked at, so I'm just now going to give you a quick synopsis of the overall picture that we found. And again, keep in mind that this is a global picture. It doesn't reflect the fact that regionally there are very, very severe stresses. So this illustrates the interlinked interdependencies on a world average. My colleague put climate in the middle. I've put energy in the middle. Okay, so you can see by the size of the arrows the nature of the linkages between the different factors that we're considering. Energy has a great big fat arrow up to the atmosphere, the carbon carrying capacity of the atmosphere. Energy production causes about 60% of the world's greenhouse gas emissions that are affecting changes in our atmosphere. The other big source there is land use change in terms of impact on the atmosphere. But if we look at the other issues, water and land and minerals, the connection to energy is much weaker. I already showed you the connection between water use to produce energy, less than 2% in energy extraction and about 9% in power generation. We can also look at the energy used to treat water. It says there less than 1% of the global energy is used for water supply and treatment. It's actually about 0.3%. If all of the most of that energy is actually used for water treatment. If the entire world were treating its wastewater to the standards of the Western world, that number would go up to 1%. If we wanted to desalinate half of all the water withdrawals that we are using in the world right now, that number would go up to 5%. Desalination is energy costly, but in fact, on this scale, it's not the biggest energy use you could imagine. Desalination, in fact, may be more costly in its environmental impacts because when you desalinate, you're left with brine, and disposal of brine is a very serious issue. Then we can look at materials. We took a look at material scarcities. What we found is that physically, most of the materials that the world is going to need in the future to produce energy are there in physical content. The problems that exist in acquiring them is that they're not uniformly distributed. There may be supply chain issues. Some minerals only exist in one or two countries. If there's political instability or a trade imbalance, you can run into issues where it becomes difficult to get those minerals. The two that we identified as important for the energy industry are rare earths. Those are used in catalysts for refining oil, and they're used in magnets for wind turbines, et cetera. And the other one was chromium, which is a very important alloy in steel. And again, those are both issues of not of natural availability, but issues of political and supply chain. And then finally, there's land. And land is a big issue. As we've heard, irrigation for crops draws about 70% of the world's water withdrawals. You should keep in mind that that is in areas where crops have to be irrigated. There's many parts in the world, of course, where you can primarily grow crops by rain feed, and then you're not withdrawing any water. Biofuels right now use about 2% of the global cropland. Our estimates are that in the future, all of the world's existing cropland is going to be needed to feed people, but we're looking forward to a future in which you can develop biofuels crops that don't have to be grown on high-quality cropland, but you can look at degraded cropland, pasture land, marginal lands, so different types of non-food crops. And in those cases, it appears likely that one would be able to draw about 200 megahectares of non-productive land into production for biofuels, and that would allow you to produce about 20% of the world's transportation fuels. So those are numbers. You can see I'm a physics professor by heart, and I like to get the numbers straight, and I think it's very informative and very helpful to underpin some of these discussions for everybody to have the same basis. So thank you for your attention.
Thank you. We always seem to end up talking water on or at least I do, on a rainy day in a water-rich place like Washington, D.C. with a river that I can see out the window, sort of. I am going to ask a question to give you all time to start lining up at the microphone. I really want this to be more of a back and forth between the panel and the audience than a back and forth between the panel and me. Although I also encourage you guys as panelists to question each other. Maybe some points of dissonance in the various presentations. So while everybody's kind of lining up, given that we're at ARPA-E, and given that the two things that people clearly care about are the price of gasoline and where their food comes from, what do we need in terms of innovation in this space? Innovation is, of course, the topic of this talk, and the corollary of that is where are we actually likely to get it? There may be a Hopefully those microphones are working too. Anybody want to take that first?
Well, is this on, or do I need to do something?
It's
on, okay.
Like it's on.
So I probably should let Molly do this one, but I think one area where there's huge innovation is in creative ways to develop biomass that will not compete with crops, and then creative ways to take that biomass and transform it into useful products. I was just at Ames, Iowa, and I saw one of their amazing projects where they're taking biofuel and treating it by a technique called pyrolysis, where they heat the biomass very quickly in a non-oxidizing atmosphere. It creates a bio-oil that can be treated to create a fuel, but it also creates a waste side product, which is called biochar. And they've discovered that biochar is very chemically inert. It does not react with just about anything, and they estimate that it will store its carbon, and that carbon will remain stored in the biochar for 1,000 years. That's carbon sequestration. Plus, the biochar has amazing capabilities for improving the quality of degraded earth. It serves for water retention, and it serves as a habitat for beneficial bacteria. So that type of innovation is very exciting, and it gives me a lot of hope.
I think one of the challenges is are finding innovations that will scale. The scale of this challenge is in fact so large that one of the big difficulties is going to be to take interesting and promising research results from sort of individual laboratories or individual sort of research teams or even collaborations of research teams, and then finding ways that they can actually go to scale. And that I think is going to be as much in a sense, sort of an organizational problem, a strategic problem, just as much as it's going to be a scientific or technical or engineering problem. Biochar is a great example. It's a very, very, the biochar has been known for a long time. It's a very, very interesting avenue of research. Whether or not that can scale, and whether or not it can scale to the degree to which it really will be important for carbon sequestration, in addition to all the other things it can do, is simply an open question, and one needs to find out. I mean, the other thing I would say is that some of the innovation we need is to understand that these challenges of energy, land, and water are not only linked to each other, but they are inextricably linked to what happens to the climate system. And so what we decide to do about the climate system absolutely affects all of these things. And we simply have to have the analytical tools to begin to understand what that interplay actually looks like.
Yeah, I'm leaving this slide up because I think it highlights that particular point. This is clearly a systems problem, but please.
So maybe I can pick up right there because I think there are obviously a host of shifts from small to large scale that can move the way these systems work. And I think it's fair to say that while the 20th century strategies we used in agriculture were stunningly successful at the targets we aimed them at, which was maximizing localized yield, there were legions of unintended but absolutely foreseeable consequences. And it was actually exactly the collision that biofuels on the landscape created that brought me into this conversation beyond my reductionist skill set as a crop breeder to recognize that the management of dynamic systems with trade-offs and synergies within reach that shift across scales, that understanding that challenge accurately in and of itself creates a tremendous target for innovation. In that's what my former students are doing instead of being professors. That's exactly where they went, and they went on farm for management tools. But there are a host of technologies and the consequences of those technologies that are going to be really important in not just improving efficiencies, which is a core part, but to understand the nutrient cycling, for example. If we were to move entirely away from livestock, on landscapes. What would the potential consequences of that be with respect to nutrient cycling? In Africa, many people would argue that for reasons that connect to soil health, we need more livestock, not less. The answer, there's not a one-size-fits-all answer, and ultimately, I think there will also be innovations connecting the choices we make in this space, energy, water, and food, to the human condition. That is, with 1 in 7 Americans receiving food assistance, and that number growing, not shrinking, there's room for and diet-related health issues growing, not shrinking. There's tremendous room for innovation as well in the whole system.
Yeah. And you know, to take it global, billions of people who are malnourished in one way or another. We do have a venture capitalist on this panel, so I'm going to take the second half of that question and direct it at him. We've heard where we need innovation. Where's the money going? What innovation are we actually buying?
Well, I mean, what I can say about it is, you know, to me, if I was going to invest in innovation, and the ones that we've invested in successfully, I would say, are ones that compete very effectively at cost parity with incumbent technologies, whether energy or food delivery technologies like animals or livestock. I don't think you can depend upon subsidies and long-term incentives and expect a technology to have long-term potential. I don't think that's going to work. When it comes to your question of high gasoline prices, the most immediate fix is probably resolving political tensions with people. But if you're looking for a technological innovation, I don't know if biofuels are necessarily the answer. You know, when I worked in Cargill, for instance, they were food first, fuel second. There's a reason for that. I mean, you know, you have to feed the world first, and if you look at the energy density of biomass feedstocks versus other feedstocks you can use, they're not so great. So, for instance, one area we invested in was in looking at more energy-dense feedstocks. Take, for example, plastics. A significant amount of plastics are discarded every single year. They're highly energy-dense because they're just reconstituted hydrocarbons. And using pyrolysis technology Alan mentioned previously to recover those into crude oil is actually not only is it a scalable technology, it only costs $5 or $10 million to enter that versus hundreds of millions, and it doesn't require any type of subsidy. So what I can say is, you know, I think, you know, in pontificating about the future, that, you know, I think there's a practical element to it that requires a return on investment and cost parity, and some of that might not allow for some of the things we wish could happen.
Right. So I see a line of 3. That's an encouraging start. So I'll turn it over to the audience.
Hi, I'm Albert Davis from the Department of Energy. Some of the problems with water is that it's not distributed evenly geographically, but also in time. So you have greater flows during certain times of the year, and the way that people have managed that is with things like dams and big water transfer projects. Okay. So the problem with the dam, of course, that water is used for a lot of purposes, and domestic uses, power, agriculture, so on and so forth. But there's a lot of evaporation behind those dams, and in fact it can be 10 to 20% of the total amount of water there is actually consumed because it's evaporated. And so when you talk about hydropower, which I don't think you really mentioned here, it uses a lot of water, and the information I have is that it uses more water than thermal power plants on a kilowatt hour basis or something. So would you care to comment on that?
I'll just say that knowing what that slice of renewables is, it is mostly hydropower and then biofuels, which are, of course, extremely water intensive. The other renewables, wind and solar, wouldn't show up if we were just showing those.
So I would comment that it's actually really hard to figure out a apples-to-apples way to compare the water used for hydropower. So the fact that it's evaporating is absolutely correct, but what that means in terms of the net impact on the basin is a little bit more complex. This is one of these really complicated systems issues where you've got more evaporation, but you may also then have more precipitation. So, but I agree, it is a water use often in a dry area.
And don't forget salmon. Salmon are important. Next question, please. And introduce yourselves. Thank you for introducing yourself.
Sure. Actually, I'm also from Ames, Iowa. Iver Anderson from Ames Lab. I just wanted to add a little more detail to the materials balloon up there, and especially as it relates to rare earths. I mean, we heard the gentleman from FedEx yesterday talking about the criticality of batteries for electrification, basically, of the industrial and commercial and consumer vehicle fleets. But it's also true that rare earths are used in the most compact, high torque drive motors for vehicles. And that is really, that's sort of the widespread, and it touches every one of our lives, actually. If you want to get an electric vehicle, or if you want to trade in your gas vehicle for an electric vehicle. But and I should say also that at Ames Lab we are also working on a vehicle technologies program to develop alternatives for rare earth permanent magnets that will permit us to electrify our vehicle fleet and use the materials that are much more abundant and much more available worldwide. So we think that the vehicle fleet problem, electrification, and the wind turbine problem are really both related, in fact, in the generator and motor side. And right now there's also a linkage coming that vehicle technologies has also established between motor makers and magnet research. And in fact, this is one thing that we learned yesterday also about the need for the linkage between designers and materials innovators. And that's one of the things that I think is going to be important as we go on, because there are alternatives to the generators that go into those wind turbines, as well as there are alternatives to the types of electric drive motors that go into the vehicles. So, it is important for all of us to innovate together, I think, and maybe comments on that sort of thing.
I would also note, interestingly, that rare earths mining in the U.S. stopped largely because of water issues. Water pollution associated with the mountain pass is the reason that the state of California said we don't want any more of that, and we moved it all to China, which then gets people like H. Lee Scott worried about getting dependent on Chinese production of rare earths.
And it is true that Molycorp did come back 7 years later and solved, basically by their development, the issues of water treatment and maintaining a closed water cycle, in fact.
Or at least we'll hope so. So electric vehicles, energy density of the battery seems to be the big hurdle there. That compares unfavorably with the energy density that you were deriding a short while ago of biomass turned to biofuels. Do you guys want to take that issue on?
Well, I can comment on Ames has like the world's leading program in rare earths, so I visited and talked to some of those people. It's an amazing place with an amazing program, and in fact, we are having rare earth development return to the United States. And I would say that if you look at that plot where I have the amount of water used for fossil fuel extraction, it would have looked very different 30 years ago. And so what has happened, as you've indicated, is that the extraction industries have wised up, gotten very careful. If there's, if there's a sufficient driver, if people care and put the environmental regulations in place, this can be dealt with. So that is encouraging.
But are we going to get ourselves into with this shift to biofuels, are we going to get ourselves into a water problem, or are electric cars going to have enough, or the batteries in electric cars going to have enough energy density to do what we want the cars to do? Okay, well, I'll quibble with your assertion that biofuels are water intensive, because again, it comes down to where you're growing them. If you grow biofuels in a place where irrigation is needed, I would say you shouldn't do that. If you grow it in a place where there's lots of water, the water is going to fall on the ground and it's going to be transpirated by whatever crop is there. And so you can grow biofuels in a responsible manner if you grow them where you should grow them.
So
One thing I'll say about that is that so I agree with that. I mean, purpose-grown plants that are used for energy are, in one sense, just like any other crop. Right? We can improve their efficiency, we can improve the management efficiency, you can grow them in appropriate places. I think this notion that we're going to grow them on degraded lands forever is simply not correct. I mean, if they're really profitable crops, people are going to want to grow them, and they will, in fact, compete for food unless we prevent that through policy measures. In the U.S., we've chosen one path. In many other parts of the world, it's a different situation. But one thing that I do want to stress is that we keep saying biofuels, and I don't think that's right. I mean, we have that. Many of us have that immediate perception because that's where the big policy pushes have been, and that's where subsidies have been, and so on. But in the long run, I think what we're really talking about are crops that are grown for energy, including combustion for electricity generation, so fuel, I think, liquid fuels is only one of the potential outputs from this kind of industry, and I think we could be looking at many other kinds of output as well. And so I think it is important to keep that in mind.
Anybody else? Or? Thank you, Ames Lab. Next up,
Eric Waxman, University of Maryland, and so this question deals with that figure, and it's probably more along the lines of what Ellen and Tony were talking about. And that really is that, for these innovations to take place, you have to have the market, you have to have the driver, et cetera. This figure changes dramatically if it becomes regional. And in urban and developed countries, the percentage it's going of water use for power production or power for purifying and transporting water is much more significant. That then also results then in more CO2 going in the atmosphere, and that addresses a global societal aspect, which is then, that results in less precipitation in places like sub-Saharan Africa. So, as a global scale, I think there's the societal fairness aspect. In addressing the problem, it's a much more regional aspect.
Comments from the panel?
Yeah, Eric, I totally agree with that perspective. I mean, we're trying, in fact, to develop tools that not only take a sort of very large regional and global perspective, but actually start to drill down to smaller regions and particular landscapes. It's one thing to say generally that a particular strategy or a particular mix of technologies and energy demands and water use and so on and so forth is an outcome of a particular set of constraints and a model simulation. It's another thing entirely to say that will actually fit, in a sense, on a real landscape, and that's where we see one of the serious research challenges. In part because it's complicated, but also in part because the data are much less solid on these local and regional bases than for big national averages.
Molly, do you have something to add?
I think I may say also this is why it's so critical in any conversation in this century to realize how important it is to keep track of scaling issues. And towards that end, this commission on which I served has offered the community, the policy community, the business community, the science community, the community that makes decisions on patches of ground, a concept borrowed from the ecological literature called safe operating space. And while that term in the ecological literature is applied at a planetary scale with attributes such as nitrogen and biodiversity and other descriptors of our planetary system, we understand ultimately we need to scale the implications of those insights down to local decision making on the ground, patch of ground by patch of ground, and aggregate our understanding of the implications of those choices now and later in a host of dimensions through time, which again is about really fundamentally reframing our targets.
So I'm curious, did BP go down to the regional level at that 20% figure biofuels that you gave earlier, that we could get to? I think you said we could get to 20% biofuels.
Yes. 20% of the transportation fuels, I think we could get to, and that includes regional assessments of where there is sufficient degraded and rain-fed land. It follows from many other assessments that have been done.
So what are we looking at? Energy crops covering Kansas, or what are we looking at?
Well, let's see. 200 million hectares. I don't know how big Kansas is. That's a lot of area, but total cropland is what, 100 million. 200 million hectares is 1,000 million hectares, I think. Yeah. So it'd be an increase of cultivated land by 20% above what is cultivated now.
And do we have a sense? Is that in Brazil? Is that in Eastern Europe?
It would be in Brazil. It would be in Africa. It would be in places where there's lots of water. Yeah. Well, we don't rotate the 1,000 million hectares that we're using for cropland right now. We'll use the same cropland management strategies. We'll have to use the same kind of development of sustainable approaches that we heard about earlier. You have to be able to sustain and maintain the land, or none of this is going to work.
Yeah, you can see the passion.
Yeah.
Food, water, agriculture. It gets people riled up. Since you waited so patiently, please ask your question.
My name is Mike Aller. I'm with the Space Coast Energy Consortium, and my question is about waste. In addition to my day job, I also teach part-time at a university, and I teach energy and natural resources issues. And one of the things that really kind of boggles my students is the amount of waste in our agricultural system. Here in the United States, we waste about 50% of the food that's produced. And that's a huge issue when you look at the energy resources that go into that. You look at the water resources that go into that. And we talk a lot in an energy conference about energy efficiency, but we don't necessarily look at efficiency of some of these other streams that we have. So how, as a society, do we incentivize behavior to reduce or come up with resources that we can help reduce these waste streams to support a better usage of the resources we already use?
Definitely something for innovation.
We actually started a company from scratch that does this, which recovers food waste and yard waste, essentially organic fractions of municipal solid waste, and recovers their energy potential and then their nutrient potential to return them as compost, essentially, for the soil. Toward 30 million tons of food waste is wasted every single year. There's a couple of reasons for this. One is a simple supply chain logistics, just shrinkage in places like grocery stores or in your own refrigerator. That's downstream. Upstream, a lot of the agricultural waste, again, comes from silage or livestock farming and waste created by that. And the numbers there are extravagant. They're huge. We have a company that essentially uses a very simple technique called solid-state anaerobic digestion to mimic the same process that occurs in a landfill, which is just an oxygen-deprived environment where you create biogas, which is a substance that's very similar to natural gas. And the technology we use, it can produce biogas that's about 70% methane. So I think on the one hand, there's technologies available easily to recover the energy potential or the agricultural potential of certainly organic waste, all throughout the agricultural chain, all the way from the farm to a consumer's home. Now, one other quick point I'll make on it, and it goes to this land use point as well, and you can correct me, scientists can correct me if I'm wrong on this, but 70% of cultivated grains and cereals today are used for livestock farming. So if you were able to replace that, to start with, you would get a lot of land back to use for other things. So if you want to look at real fundamental inefficiencies, you can talk about changing around the edges and recovering waste and all that other stuff. Those are good businesses, and we've built some businesses doing that. But if you want to make a fundamental change, I think you have to look at how we consume things and get to a more basic scientific level and try to solve that problem if it can be solved.
That's a huge social challenge you've just posed, changing our meat eating habits.
Right. So I want to come to this question that was just asked and come back to this notion of innovation, and this is sort of institutional innovation. Many of us are either on university campuses or part of faculty. Our own institute, for example, is both part of the National Laboratory System and part of the University of Maryland. The universities, it turns out, can be used if there's appropriate leadership as a really interesting sort of set of innovation experiments, not necessarily commercial innovation experiments. They're mostly not in it to make a profit, but they can try some interesting things that I think have real potential for the creation and nurturing of companies. And so I'll just give you one example that I happen to know of, and it actually is one of Molly's former professors when she was a dean, is now provost at the University of New Hampshire. And he has taken the University of New Hampshire pretty much off the grid. And the way he did that was by constructing a series of agreements and then having local companies essentially create a stream of gas from landfills into the university, and that's what they burn for heat and power. And so they're not completely off the grid, because the university is a big sprawling place and it's cold in New Hampshire this time of year. But they have gone a long way towards essentially being self-sufficient by using a waste stream that otherwise would have either been vented to the atmosphere or something else would have happened to it. And they've essentially, it's not that they've reduced the waste stream, but they found another way to use it. And that's a really interesting example that, and there are many, many other examples like that out there.
From a systems perspective, though, aren't they relying on food waste to kind of get that gas in the first place?
Relying on all the things that go into municipal solid waste.
Molly.
So maybe I can circle back and use my canonical dairy farmer as an example of someone who's thought very, very carefully about that challenge in place and has considered carefully all of the outputs that would have been characterized as waste, and really in a systematic way thought about how to convert his operation to turn that waste into something of value, and to whatever's left, manage that appropriately. As far as waste, obviously he's made a huge investments that have more or less paid back in energy and converting manure to energy. He's dropped his electric bill at least 50%. One thing about John is he doesn't measuring. It's a little bit hard, but his electricity consumption's dropped incredibly. And his goal is to go off the grid, a dairy farm off the grid with that many cattle. Another exciting thing that's happened in dairy in particular is the fractionation of milk into valuable milk products. We used to dump whey in the field, and now sometimes whey is more valuable than lots of other things about dairying, and is moving protein around the planet. But beyond that, I think there is a really important point to make about waste and externalities of agriculture. To the extent we fail to reflect in the cost of doing agriculture, the planetary costs, waste is tolerated in ways that I think we are going to have to revise and revisit. And this really circles back to a point I want to emphasize about innovation, which it is not, we focused through the 20th century very much on productivity and waste, and not management of waste. But in this century, the management of risk as well as systems is going to be really important. And if we think about waste, especially in food systems, food safety has been sort of an unconstrained mandate with implications for food waste. I think we're going to see the need for much more refined consideration, much more detailed consideration of the dynamics connected to the imperative for food safety and its implications for waste. And I think there may be opportunities for innovation in technologies and the deployment of those technologies with a more complete recognition of the value of those technologies beyond simply waste reduction, as that literally alleviates some of the pressure agriculture places on the planet.
It's interesting. Cheap food, which is what I think you were referencing there, combined with cheap energy / cheap refrigeration, is what led us to this point of 50% thrown away every year. So again, systems. Thank you. Next question.
Hi, I'm Janetos. I'm based near Cleveland, Ohio, and I've just joined a startup based in Israel called Univerve. First, just an elementary question to understand some of your statistics. how do you distinguish between water withdrawal and water consumption? And secondly, if I may, I'd like to just present a general question to such a diverse and distinguished panel. How do you regard the potential of microalgae as a fuel or energy source, particularly in a system that makes use of land unsuitable for agriculture and wastewater or salt water instead of fresh water?
Thank you for asking a question that was on my list, too.
Maybe you want to start? I can answer one of them, but maybe you want to start.
I was just going to do the withdrawal.
Yeah, let's start with withdrawal consumption.
Okay.
Let's get that clear for everybody.
So withdrawal is the easiest water number to measure. It is simply how much water you take out of a river, a lake, or an aquifer. And so that it happens to be the one that has the best statistics. It's easiest to quantify. And it does correlate very well with water stresses and impacts, even in cases where the water is not consumed. So in an electric power plant, you draw out a lot of water, you evaporate a very small amount of it, and then you put the rest back. And so you would only count the amount that was evaporated as consumed, but it would be incorrect to think that the fact that you've taken it out and then put most of it back is insignificant. It really has a significant environmental impact, including in cases where the rivers might be running low in a dry season, or you just are losing water flow altogether. So we use withdrawal because it's the easiest one to measure and the clearest one to talk about. And the other numbers of consumption, and there's some other measures as well, sometimes water gets used more than once, are just much harder to quantify. But this gives us the big picture.
Yeah, and withdrawal can be kind of seen from space, where the Colorado River, no longer reaches the sea. Many other rivers no longer reach the sea. On to his second question, algae.
Your question about algae.
Obama.
Okay, so I don't think algae has very much potential at all for fuels. Probably I don't know if that's a good thing to say or not at ARPA-E, but this is I think people are interested in it because of its photosynthetic potential, but it's 1% solids. I looked at this every which way, and I think there's probably more business plans received by people like me for algae and different configurations of algae, whether for fuel or for other purposes, than almost anything else in the biofuel space. And I think that's also an indication of things. But it's just hard to figure out how an organism that's like that, how you're going to end up recovering useful fuels from it, especially when you have to remove that much water, the hydraulic load of all of it. And then at the end of the day, what is the ultimate cost, right? And I've never seen a cost model for fuel and algae that came anywhere close to being reasonable. And you asked a question before of the cost of gasoline, because cost is what matters. Now, to the question of does it have potential for other things, I think it certainly does. I've seen applications of algae for wastewater treatment or water treatment that seem pretty compelling to me and have commercial potential. I've seen applications of it for recovery of nutritional value, like nutraceuticals, that seem to have a lot of potential as well. But I think where it has potential is for those higher value applications, not for, say, a commodity like fuel substitute.
Maybe I can just make a quick comment about the role that algae plays on a dairy farm. It is, again, just exactly as Amol has described. It's used to scrub waste CO2 and clean up phosphorus in wastewater. It's then recycled back in as animal feed primarily. So it's in on-farm use. It's not necessarily energy, but it adjusts the energy balance of the overall operation. And for particularly wastewater, it's a very interesting use. I can tell you it's quite something when you're dean to have somebody show up with a mason jar full of green stuff in your dean's office. But I think it's certainly it has certain capacities that are really significant to look at in light of systems.
And you can see some of those vials downstairs in the showcase if it's not already closed. I wonder if I can ask you, Ellen. Some of the oil companies I know, certainly ExxonMobil, perhaps others, including BP, have made fairly significant investments in algae. What do you see that maybe Amol doesn't?
Yeah. Well, BP is not investing in algae. We're keeping a close eye on it, though, because I wouldn't completely rule it out. So it's worth looking at, but I don't see high potential for exactly the same reasons that Amol pointed out. I think high value chemicals quite likely.
So that's why ExxonMobil's in it. Next question.
Thanks. My name's Andy Gould. I'm from Fisherman's Energy. We're in the offshore wind energy development business. I was going to ask you about the 200 million acres, but instead I'm going to ask you about the dairy farm instead, if you don't mind. I think you said, I caught your name as Molly. In what sense is that sustainable? You take corn. Corn is grown largely with the addition of large amounts of inorganic nitrogen that's produced from methane. Take the corn, transport it to the dairy farm, feed it to the cows, turn it into milk, and probably with 2,800 cows, I'm making a wild guess, it's 100 tons a day of manure, something like that, ropely?
Don't know that number.
Let's say it's 100 tons a day. You convert some small part, you take some small portion of the manure and you put it in that agroponic, or the thing you showed in the picture there where they're growing the row crops under a shed. You convert some small portion of the manure into fertilizer, so you're absorbing it at an agronomic rate that probably is comparable to the agronomic rate that you would find in, the area around it. So you haven't really gained anything there, and you take the rest of it and you burn it. So it sounds to me more like you've just increased the carbon footprint of this dairy farm. You've taken something that was on the grid and had a moderate carbon footprint, and now you've taken it off the grid and now it has a huge carbon footprint. And I'm curious what your definition of sustainability is.
I'm not going to get into the details of the way this farm is managed, but feed is grown typically on farm. Mm-hmm. And so the way this system works is much more integrated than you would describe. I think we all grant the fact that there are negative environmental consequences of agriculture, of any phase of agriculture, but the point is to minimize working with the system so that there's as little waste as possible that's released in ways that create ongoing burdens. And
I don't mean to be curmudgeonly. Where is there minimization in that system? I'm trying to see where it doesn't violate either the first or second law of thermodynamics, and you actually are gaining something. Where is the gain?
Well, the gain is particularly focused in waste, right? So instead of dumping manure onto fields, which most of our dairy farms do grow their own feed, so it's a relatively closed system with respect to at least some aspects of feed and manure.
Nature intended manure to be dumped on fields.
Absolutely.
I mean, of course it didn't intend. It can only be absorbed at an agronomic rate because of the concentration.
I'm going to jump in here because there are more questions.
Thank you.
But if you want to.
But I'll tell you one very positive thing. He would love better technologies to measure what he's doing and what its consequences are. Mm-hmm. Because he has made a lot of common sense improvements. He can see drops in costs, improvements in profitability. He can estimate that certain choices he's made have positive benefits. But our ability, and this is really where my former students are coming in, our ability to make sure we're not making mistakes while we're doing things that are rewarded in the current economic structure, or at least neutral, is more limited than it should be in this century, given the challenges we understand both enterprise by enterprise and in aggregate.
Okay. Yes, sustainability provokes a lot of passion. This reminds me of some of the arguments I've seen around local food and kind of the strong desire for local food to get away from transportation issues when, maybe transportation isn't that big of a deal when you look at all the energy.
We also, and I'm going to say one more thing, we also have a history of boondoggles in this and related areas. We all remember what Jimmy Carter tried to do with syngas, and it cost the taxpayer billions of dollars. We all probably remember that 5 years ago, carbon sequestration was presented to the public as a panacea, and now, thankfully, it really isn't being talked about, I don't think, as much as something that's going to be a solution. I mean, people still talk about it, but it seems to be disappearing. But there's a history of boondoggles, and that's why I'm curious about this. But thank you very much.
And some would argue that offshore wind is also a boondoggle.
Hi. My name is Diego Acevedo. We have a startup company called Blue Rise, and we're working on ocean thermal energy. And working on ocean thermal energy, then we start studying what we can do with the ocean and with the water, and we can see that there's much more uses than just power generation, right? And we can use the deep sea water for some technologies that are out there on seawater cooled greenhouses or innovative aquaculture techniques. And this can be done, obviously, in the tropics where some crops can't grow or some fish don't naturally grow. So you could supplant this type of food production in a way. and have some sort of desalination techniques. But you can also think of the same cooling effect from deep lake cooling, which hasn't been mentioned. So the use of water from lakes or the ocean for first energy efficiency, but also to help some of these agricultural techniques in some sort of greenhouses that use cooling instead of just warming in certain regions, right? Because this is a global thing, and certain regions work better than others. Yeah.
And we have about 5 minutes left, so I want to get all the 3 questions that are up there, and maybe we can answer them all together.
Bill Clinton.
Very quickly.
Okay, so Bill Clinton said, it used to be Freon was the big greenhouse gas, and now it's methane. And I understand where methane comes from landfills, but he said the other big source is agriculture. If you guys could tell me, A, where it's coming from, or are you investing in anything that either captures it or prevents it?
Okay, and the last question.
Kelly Zering, North Carolina State University. First of all, I wanted to make a comment about scope of the problem. You talked about a 30% global population growth, but there's 100% increase in quantity of food demanded anticipated. And I'm wondering about the energy forecast, if that includes this rise in income that's driving consumption growth. The second comment, the question, I guess, is are you considering innovation in biology as you're making your comments? And there's some tremendous developments occurring in the genetics of various plants. So, thank you.
Sorry, those were the last questions. I apologize. You can get us at the end. So who wants to tackle what first?
I'll start. The big methane sources are methane from landfills, from a whole host of natural sources, wetlands, and livestock. So livestock are a huge source of methane. So is rice cultivation, and those are probably the 2 largest anthropogenic sources of methane. So the issue about do we take into account improvements in biology and sort of rises in wealth, when we do the integrated modeling, we absolutely do that. Certainly the rise in incomes and wealth part we can specify, or we can allow the models to produce that. We take into account biology in 2 ways, and one is by the details of the technologies that we try to represent in the models. So for bioenergy crops, for example, we don't even bother modeling ethanol from corn. We actually go right to 2nd generation, and we're trying to figure out how to do 3rd generation bioenergy crops, because we're not concerned with trying to model the next 5 or 10 years, and so we've already started to do that. We also try to explicitly take into account what one could reasonably expect for increases in per hectare agricultural productivity. And there we're guided by 2 things. And one is what the historical record has shown. The second is what a whole body of experts, international experts, believe is possible. One of the big challenges right now is that most of the investment into crop genetics is not going to increase yield. It's to make it, Roundup Ready soybean doesn't increase yield. It reduces costs, but it doesn't increase yield per hectare. And so most of the actual investment right now is going into improving the efficiency of management and cutting down on the amount of amendments that you have to do, but it's not necessarily hitting the big yield challenges, particularly in parts of the world that need them to happen. Whether it's 50% or 100% increase in demand that we're going to see, depends on which expert you talk to, but there are big increases that we're going to need, and right now it's not clear where they're coming from.
Maybe I can just quickly hit on both points. Methane, again, Tony said it, it's rice and livestock in general, and really of those producer-driven sustainability initiatives, dairy is out way in front of many of the others, partly because they have a checkoff system where they tax themselves to create investments focused on research to serve the industry. Front and center in the Dairy Sustainability Initiative are strategies to both measure and manage greenhouse gas emissions from dairy, including enteric emissions, where methane comes from. So there's, I think, some very interesting science coming from shifts in feed to the various comments we've made about the interactions between choices with respect to land management and animal-based outcomes, feed amendments, and the role that grazing systems may play in managing these dynamics connected to methane emissions from livestock systems. With respect to genetics, Tony points out we've had a pretty consistent rate of yield gains over the last number of decades. In many cases, we're starting to observe a very concerning flattening of that rate of gain in crops. And Tony points out it may be a direct result of reduced investment in precisely that category. That said, there's tremendous advances potentially within reach connected to moving yield potential. However, a really important additional focus is closing the yield gap, particularly in the developing world, with respect to the ways in which genetics may be deployed. And finally, I can say I'm teaching a graduate seminar now in plant breeding for 21st century agricultural systems. Those genetic advances are not just about crops anymore. We're really looking at the ways in which genetics can influence our construction and management of overall agricultural ecosystems, including the management of ecosystem services.
We are out of time, and free drinks are coming. We didn't even get a chance to talk about climate change and its impacts on the water cycle or crop yields. We didn't get to talk about desalination too much. There were lots of topics we didn't even touch on. I want to thank the audience for your kind attention and great questions, and I especially want to thank the panel